Good afternoon. My name is Jasper. I am excited this year to provide a status update on COBIA, as a lot of progress has been made. In this presentation, I will talk about marshalling and threading, and I will give a short demonstration of marshalling. I will talk about the COBIA threading models and how they relate to the COM threading models. For those of you that are new here, COBIA is CO-LaN's new middleware. Until now, COBIA supported two middlewares, COM, which is specific to Windows, and CORBA, which requires a particular ORB software to be installed. So far, nearly all implementations are based on COM, and therefore they are bound to Windows. COBIA aims to lift these platform restrictions to simplify COBIA interoperability and authoring, and increase the efficiency and reduce errors by the use of stronger typing. There have been several presentations on this, so I will not elaborate too much on what COBIA is. Today is about marshalling, and related to that, threading. Marshalling is usually not needed, which is a good thing. Here's a very simple picture. We run a process modeling environment, a PME, with a process modeling component in a dynamic library, and they are compatible. So the PMC is loaded in the PME directly, and the PME can directly call the PMC. So far, so good. But sometimes the PME and the PMC are not compatible, for example, because they have different threading models. I will explain this later. Now the PMC can still run inside the PME, but must do so in a separate thread. Hence, there needs to be a communication from and to this thread, and this can be done by marshalling. Sometimes this communication is not needed because the threading model is incompatible, but rather because the memory model is incompatible. Take, for example, .NET and native implementations. Native implementations consist of machine instructions. Native applications cannot directly access .NET memory and vice versa. Somebody will have to do the translation, and that would be the marshaller. Sometimes the PMC cannot run into the PME process at all, for example, because the PME process is a 64-bit application and the PMC is only available as a 32-bit implementation. Now we have no choice but to run the PMC in a separate process, the host process, and again we have the task of setting up the communication between the PME and the PMC, which is now hosted by the PMC process. Each top-level box in the schematic defines a separate process. Perhaps it's technically difficult or impossible to implement the PMC in a shared library, and in that case it could be implemented in its own executable, which then of course cannot run inside the PME executable, and again marshalling is needed. So far, we were assuming that the PME and the PMC run at the same computer to begin with, but we can also lift this restriction, and it might be useful for example, IP reasons or licensing reasons or technical reasons to run the PMC at a different computer altogether. Clearly, all marshalling will impede on performance to begin with, and even more so if you're talking about a different computer. So I do not see this to be a particularly useful scenario for the most commonly used PMC, which is a property package, but it could be a very useful scenario for a unit operation PMC that internally uses its own thermodynamics and therefore does not require a lot of communication. In this case, it doesn't have need to run on the same operating system. It could, for example, run on Linux. Again, we will need the PMC host process on the host computer, and this will have to communicate with the PME process, which is done by the marshaller. We can use simply, of course, unsecured TCP/IP if the host is inside a trusted network. But if the host is not inside a trusted network, we have to deal with authentication, firewalls, secure sockets, and whatnot. We are planning to route such traffic over a secure shell connection. And finally, sometimes none of these scenarios that require marshalling hold true, but we still want to sit in between, because we want to make a log of the communication, which could come in very handy for developers, or even for developers to ask the end user to produce a log of the communication between the PME and the PMC to troubleshoot. So briefly rehashing the need for marshalling. Marshalling is needed when a direct call cannot be made, either because the PME and the PMC do not live in the same process, or because they have incompatible threading requirements, or because they have incompatible memory requirements. Marshalling requires the proxy object that represents the actual object on the other end of the connection. It requires transport, and it requires synchronization. A direct function call between two objects could look like this. The function call is made by the caller, and the callee processes the call and returns the function's output. The caller could be the PME, and the callee could be a PMC object, or the caller could be the PMC, and the callee could be a PME object. When we have to marshal, the situation is slightly more complex. Data needs to be transported over the separation between the two memory spaces, which is indicated by the gray line in this picture. To get there, the caller calls the client proxy object, which represents the object on the other side of the connection, and implements the interface that is being called. The client object provides the marshaller with the necessary information for the remote call. The marshaller will then pass this information to the host proxy, which knows how to call the actual object that is being marshaled. The call is made, the host proxy feeds the return values or the error back to the marshaller, which in turn feeds it back to the client proxy, and the call returns. Note again that in this picture, the caller can be the PME and the callee can be the PMC, which is the case for any PMC object that is being marshaled. Or it could be the other way around. The caller could be the PMC and the callee could be the PME, which is the case for PME objects being marshaled, such as the material object or the simulation context. The client and the host proxy objects are generic, but the interfaces are not, as they need to know about the signatures of each of the methods on the interface. So the client proxy object and the host proxy object actually use a tear-off interface implementation, where the tear-off interfaces are created on the fly when needed, as shown in this image. By choosing a tear-off design, each client proxy interface and each host proxy interface implementation can be independent of the context in which it appears. So a proxy interface for ICAPE identification does not need to know whether it's the ICAPE identification of a unit operation, for example, or of a parameter. The picture becomes even more complex when we realize that the callee in turn may call back the caller. This is illustrated here where the PME calls the calculate function of a unit operation. The unit operation asks the material object to calculate a property. The PME then forwards this call to the property package. The property package, in this simplified representation, calculates the property and calls the material object to set the property result. And then the control returns to the property package, which returns the control to the PME. The unit operation must call the PME again to get the property result. Control finally returns to the unit operation, which surely does a bunch of more work before it's returning control to the PME. Now consider for a moment a scenario where we have two of such setups. We have two PME threads, each of which allocated a property package and a unit operation. In this example, the unit operation and the property packages are bound to their own thread, for example, because they use thread local information or their apartment threaded COM object. As the PMC host process is not aware of the threading arrangement of the PME process, one possible arrangement is that each PMC thread contains one property package and one unit operation, and it could be that they are placed in such a manner that the property package in thread 1 is associated with the execution of the unit operation in thread 2 and vice versa. What follows from here is that while the unit operation A is executing a callback in the PME to do its thermodynamic calculation, it must process unrelated incoming requests from the PME, in this case a request on the property package B, or else the whole system will deadlock. This does not hold for the PME side. All calls on the PME side are synchronous, which you would expect because that would also be the case if no marshalling was used at all and the PME is unaware of marshalling. As it is outside of the scope of this presentation to go into all the technical details of marshalling, and as there are far too many and too complex to discuss here, if you are interested, you could contact the Method and Tools Special Interest Group for the specification document, which is available, and the implementation details all show from the actual COBIA source, which is available to all CO-LaN members. So I'm going to present a small demo for marshalling where the 64-bit thermo-client PME test and the 32-bit water property package, both of which were deliverables of COBIA Phase 2, are used in an unmodified manner in a marshaled scenario. This is of course out of process because the 32-bit and the 64-bit objects are incompatible to run inside the same process. We're going to use precompiled client and host proxy interfaces, and we'll use the TCP/IP loopback device for the transport. The video I'm about to show features our COBIA demo thermo-consuming command-line-driven 64-bit PMC on Windows. It will use the water example property package, which is, on my computer, only registered for the 32-bit x86 platform. So COBIA knows it should start a 32-bit PMC host and create the PMC in there. Then the PME will ask for a phase equilibrium calculation. During this calculation, a lot of things happen, and one of the things that happens is that the PMC is required to set the list of phases at equilibrium at the material object, which of course lives on the PME side. So that callback has to go over the marshaller. Now remember that the PME calls calc equilibrium not directly on the object, but on a remote representation of the property package, which is the client proxy. Then the marshaller passes the call on to the host proxy, which actually makes the call. Then the host proxy returns control to the client proxy. For the material object, it is the PMC that talks to the client proxy, and it is the host proxy that talks to the actual material object implementation. To illustrate that all of this is indeed happening, I will set a breakpoint at both of the client proxies and both of the host proxies, so 4 breakpoints in total. We will see the PME initiate the call to calc equilibrium, and we will see the PMC host making the call, and we will see the PMC host initiate the call to set present phases, and the PMC side modular actually making the call. So there goes, here comes the video. So I've set up the debugger to automatically attach to the child process, which will be the PMC host process. What we're going to execute is a calc equilibrium call, so I've also set 4 breakpoints. I've set 2 breakpoints on calc equilibrium on the host proxy interface side and the client proxy interface side, and I've set 2 breakpoints in set present phases, which is being called during calc equilibrium as a callback from the PMC into the PME. Let's execute the debugger. You will see that if I load the 32-bit version of the water property package into the 64-bit process, the debugger here is doing a bit of work because it has actually loaded all the symbols on the second process. So now let's go to flash calculation and actually execute the flash. Now we see that indeed the debugger will hit into the breakpoint of the client proxy interface side in the PME process, which sets up enough information for the marshaller to execute the call, and then it's asking the marshaller to execute the call. This call will arrive on the PMC process in the host proxy interface implementation, where the information is being unpacked and the call is being actually made on the marshaled interface, during which set present phases is being called on the host side. So in this case, the host proxy interface lives in the PMC process because it's a callback into the PME. The information for the call is being set up, and the host proxy interface is asking the marshaller to execute the call. When this is done, the PME process suddenly receives an incoming call, and it will then execute the call on the material object while the calc equilibrium is still on the call stack. So once we finish this process, the flash is actually successfully calculated, and this demonstrates that a 32-bit PMC can at this point be called from a 64-bit process. So these proxy interface objects look quite complex, but it is important to realize that these are not actually written by hand. The ones that you were just looking at are generated from the COBIA code generators, from the type information. This will be part of the COBIA runtime distribution for all CAPE open types, all the types written by CO-LaN. Software vendors can of course also write their own custom types, and code generation for this is also in place. The type information for all of this must be put into the COBIA registry, and this part has also been done. And of course, this greatly benefits other code generation tasks as well, because you no longer need to supply the IDL for any type that is in the registry. As a backup plan, we plan to make proxy interface implementations on the fly. Prototypes for this were built for native code using the foreign function library, and for .NET simply using the reflection capabilities. Let's have a quick look how this works for custom types. Custom types are interfaces that are designed by software vendors, as opposed to the interfaces designed by CO-LaN, to make public some functionality of their software. It all starts with defining the types themselves in the interface definition language, in the IDL. And then for platforms on which the vendor knows that the software is going to be run at, the vendor can provide optimized and precompiled proxy interface factories in the form of dynamic libraries. The source code is made available from the code generators itself, so you don't have to write that by hand. Of course, you still need to tell it about the types, either by passing the IDL or by registering the types and telling the code generator which library to use. Then the software vendor at installation time should register both the types and the precompiled proxy provider. Now when a marshalling situation comes along, the marshaller can check in the registry for any precompiled proxy interface providers, and if it's there, it can simply load them from the DLL and use them. Of course, because COBIA is an interop standard, it is possible that the interfaces are used from a context that the software vendor did not foresee, for example, remotely from a different operating system or from .NET. For this, in a later stage, we will provide on-the-fly, just-in-time proxy generation. For that, we can use the foreign function interface library for native code and for any languages that support reflection, such as Java, Python, and .NET. We can use reflection. The type information, of course, is required also here, so it is important to register these custom types in the COBIA registry at the target computer at installation time. Okay, so a few words about threading. COBIA has two threading models. A threading model is a set of agreements that the PME and the PMC must both abide to make sure that there's no unexpected behavior. For unrestricted threading, the PME has access to all PMC objects from any thread, as long as it takes care not to do so concurrently. If a PMC cannot deal with this, it can request to be of the restricted threading type, in which case the PMC can be accessed only from the thread in which it was created. Please note that this is not the same thing as single threading, because there still may be multiple threads, each of which contain PMCs. So not concurrently. What does that mean? Cape open objects have a state, so it does not make sense to call a cape open object from multiple threads at the same time. A unit operation, for example, has ports and parameters. All of these are part of the state, and it makes sense for the entire unit and all of its ports and parameters to be accessed non-concurrently. Obviously, you do not want to reconnect a port while the unit is calculating. Similarly, you do not want to allow setting a parameter value while the unit is calculating. A less obvious side effect is that you cannot monitor parameters from a concurrent thread while executing the unit. Still, this makes sense, or else the unit operation would have internally need to shield the parameter value, which is a level of complexity we do not want for software vendors. So not accessing a PMC concurrently applies to the primary PMC object and all of its secondary objects. So if the PMC cannot do unrestricted threading, something needs to give. The PME can indicate when creating the PMC that it does not need unrestricted threading, because it will only call the PMC from the thread it was created in to begin with, for example, because the PME is a single-threaded application. If the PME does not actually indicate this, then the PMC will have to be marshaled over a single in-process thread. This too is in place, be it currently suboptimal, because we're using the generic TCP/IP transport and the generic marshaller, both of which can be done in a more optimal manner, which we will do in a later stage. Of course, we also have to deal with COM. So for the creation of COBIA objects from a COM PME, COBIA knows what to do. There are no issues here, because in a single threaded apartment, the COBIA PMC will be created as if unrestricted threading is not needed. Otherwise, it will be created for unrestricted threading, leading to in-process marshalling in the case the PMC requires restricted threading. When creating COM PMCs from the COBIA PME, the situation is not that clear, as COM needs to be initialized on the thread, specifying the COM threading model for the entire thread, not for the PMC, as we do for COBIA. We have two solutions on the table to choose from to make sure that this interoperation will go without costly marshalling when possible. One of these solutions may be more optimal in the long run, when we expect COBIA to be more prevalent in the Cape Open world. The other one would be more optimal in the short run, where we have to deal with the current ecosystem of mostly apartment-threaded COM objects that currently exist. To be able to get the most optimal design here, we might require your feedback. We can draft a proposal outlining both the alternatives, and we might submit it for a request for comments. So be prepared for that one. So let us see where we stand, what the status is. Let's go back to the slide about marshalling. Clearly, unmarshaled in-process interoperability works. It already did in COBIA Phase 2. In-process marshalling due to threading incompatibilities currently works too, but with the generic TCP/IP transport, which is not the most optimal. So we still need to put a more optimal implementation in place there. Native .NET interop does not work because we do not have a .NET language binding, but the groundwork for that is of course laid. Logging does not work yet. This is scheduled to be taken care of at the end of Phase 3. Out-of-process marshalling works, but again with the generic TCP/IP transport module at this point, we can do better than that, and we will. On Windows, it will be replaced by a shared memory implementation. Marshalling between a PME and a PMC that is implemented as an executable has not yet been done. Clearly, also here the ingredients are in place, but the protocol of creating the host process still needs to be designed. Even though we have not released anything officially for Linux yet, COBIA runs fine on Linux. So those of you that are CO-LaN members have access to the source using cmake, make install. You're good to go. As TCP/IP works, it will be small trouble also to implement a PMC service host, which we did, and it works. So again, this is the generic TCP/IP layer, which is currently in place. So the transport is unsecure. If we want to do this for untrusted networks, we still have some work to do on the secure shell interoperability there. So as you can see, the basic generic marshaller with the basic generic TCP/IP transport that has now been delivered makes a lot of scenarios work already. Here's another quick demo just to show that the Linux Windows interop is indeed working. So on the left side we see a DOS box, on the right side we see a Ubuntu command prompt which runs on the same machine under the Windows subsystem for Linux. If on the Windows side we ask for the registration of our water property package, we can see that there's only one service, which is the COBIA protocol on the localhost at port 5813. So now we can start the PME. There it is. If we try to create our property package at this moment, it will, after a while, simply time out and say an unspecified marshalling error. This is because we actually have no service running at port 5813. Let's start one on the Linux side. So I've set up the debugger to start the service and create a breakpoint in property package H at line 44, which, as you can see in the COBIA repository, is the line on which calc equilibrium is implemented. So let's start the debugger, and from the debugger let's start the service. As you can see, the service is being started at port 5813. So now we go back to the Windows side and we recreate our property package. This time it not only succeeds, but we also see on the Linux side threads are being created to host the property package. The function that we're going to execute is a flash calculation. So at the moment we execute the flash calculation, we indeed see that a breakpoint is being triggered on the Linux side. Let's have a look at where that is. It is, surprise, surprise, in calc equilibrium, which is where we set the breakpoint. So we do indeed see that the breakpoint is successfully being executed at the Linux side. If we now continue executing, it will finish the flash calculation and the results will be sent to the Windows side. And we have now successfully calculated a flash in a Linux-hosted property package from Windows. So to conclude, we have seen marshalling in action. This is a very important milestone in COBIA, and it sets up for cross-architecture, cross-language, and even cross-computer interop. Some details on the COBIA interop and threading models remain to be worked out. Last year I stated COBIA was cool. This year COBIA is a lot cooler. Please try the code that is there. We're working very hard to make Cape Open better, and COBIA is being a substantial part of this effort. Based on our early experience, the benefits of these efforts are exceeding our expectations, but please verify this for yourself and provide feedback to us where you can. Thank you for your patience to sit through this. I'll be happy to answer your questions.